So we're going to look at a question that's a very common AP question, and I'm calling it clay blob thrown at a stick. Maybe I should have even done this in the last video as my example problem because AP does this question all the time. So what you have is you've got a clay blob here. The nice thing about drawing clay blobs is they don't have to look nice. It's got squiggles everywhere. Like, I meant to do that. Thrown at a stick. And so the pivot point for the stick is going to be here. So when this clay blob is going to come, and we're looking at it from above, so I'm not going to worry about gravity. So it's just going to hit it and spin. It's like, because, you're looking down on it, gravity will point this way. Okay, so I want to know what is the angular speed of the stick after the collision. So I guess let's do the givens first and we'll write that down. So mass stick, let's say, is let's say the mass of the stick is 500 grams again. So 0.5 kilograms. The length of the stick, let's say it's a meter long. And that's just for consistent notation. It's initially at rest, and so its moment of inertia, because it is a stick rotated about one end, is going to be 1/3 ml squared. Now for the clay, we're going to say that the mass of the clay is going to be 0.2 kilograms, 0.25 kilograms, because apparently I wrote 5. And then the velocity of the clay is going to be, if you're throwing it, let's just say 10 meters per second. That's a nice number. And it is going to hit at the end of the stick, so a full ls away. So we're going to say R equals ls. Okay, so the question we want to know is what is going to be the angular velocity of the stick. So in this case, we don't have to worry about linear velocity because it's fixed at a pivot point. So we can just say everything's angular. Now, its center of mass isn't going to be moving. It moves in a circle around the pivot point, but it's not going to be moving down a line. So the question we're asking, like I said, is what is the angular velocity after the collision? Okay. So let's go ahead and do this one. If you guys want to pause it now and try it on your own, you are certainly free to, and even encourage it. So looking at this, I'm going to start the same way I do every other angular momentum problem, and every other momentum problem really. I'm going to say that my initial momentum is equal to my final momentum. So now I should ask myself, what is the initial, right? Give myself a little bit more space. Well, the initial is r cross p, because this guy is moving in a straight line, so I'm using this for angular momentum. And my final is going to be I omega. But once again, this is going to be an inelastic collision. That's why we're doing clay, because it's going to hit, it's going to stick, and it's going to wrap around. So this is not just the stick, right? It's going to be total. I want this to be, let's put a T there for total. So I want this to be I stick plus I clay times omega. So what are we going to do for the moment of inertia of the clay? Let's just nail this down since we're on that subject. Well, the clay is a big ball and it's going to wrap around, be vaguely ball-shaped. So we can consider it like a point mass. So what the moment of inertia of a point mass is just mr squared. So we're going to say IC equals mass, clay, and our r in this case is distance from the point of rotation, so that's going to be length of the stick squared. Sound good? Okay. So now, since we're looking for omega, we can go ahead and either put our substitute in here or we can divide. I'm just going to substitute in here because, frankly, I don't like to have things in division very much. So it's going to be length stick cross mv, mass clay, velocity clay, equals moment of inertia of the stick, we said is 1/3 ml squared. Let's put an s there just for consistency. Plus, not 1, just m clay ls squared times omega. Hey, those ls are the same, so I can pull those out if I want. Oh, hey, there's an ls over here too, so I can cancel those in a minute. I'm going to pull them out first just so it's a little bit easier to deal with. So this is going to be 1/3 ms plus mc times ls squared omega. And ls mc vc. And since every angle is a right angle, I don't need to worry about that sine theta term. So now this ls and the squared term are going to cancel out. And let's go ahead and write it one more time. Dividing, sorry, I keep shaking it. Dividing by this sum of the masses here to solve for omega. mcvc over 1/3 mass stick plus mass clay times L. Alright, so now we're in calculator territory. Let's put numbers in. So once again, if you want to skip ahead and see the result, you are completely free to. Or you can watch me do calculator work. Okay, so I've got my calculator. So let's go ahead and write the numbers down. So mass of the clay we said was 0.25. Velocity of the clay we said was 10 meters per second. Mass of the stick is 1/3 times 0.5. Plus mass of the clay we said is 1/4. And then the length of the stick is 1 meter. Oh, I didn't write the units down here. Kilograms. Kilograms. Okay, so now it's calculator time. So I want 0.25 times 10 divided by, parentheses in there, I don't know if I got the first time, 1/3 times 0.5 plus 0.25, close parentheses. I'm not going to bother multiplying by 1 because why would I? And that's equal to 6. So our final angular velocity is going to be 6 radians per second. Just go ahead and slide that to the side so you can see. Alright, that's it for this video, guys. I'll see you in the next one.